Hello and welcome. In this episode, we're unlocking the secrets of one of the most famous theorems in mathematics history, Pythagoras' Theorem. Before we can jump into the theorem itself, there's a few important definitions to cover. An angle that measures exactly 90 degrees is called a right angle. This is one of the most fundamental concepts in trigonometry, and it is often symbolised by a small square placed in the angle's corner. Right angles are a key component in various geometric shapes, including rectangles and squares. Building on this definition, a triangle which contains a 90-degree angle is called a right angle triangle. When applying Pythagoras' theorem, it's crucial to confirm that we're working with a right angle triangle, as the theorem exclusively applies to this situation. If the triangle is not right angled, then Pythagoras' theorem cannot be used. In a right angle triangle, the side across from the right angle is called the hypotenuse. The hypotenuse will always be the longest side in the triangle. Let's take a moment to test your knowledge on these important definitions. Now that we have the necessary background knowledge, let's look at the statement of Pythagoras' theorem. In a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. To formulate this mathematically, it helps to work with a diagram. Given a right-angled triangle, we can label the hypotenuse as h and label the other two sides as a and b. Pythagoras' theorem states that h squared is equal to a squared plus b squared. Let's see some examples of this theorem in action. Consider this right angle triangle. One side is labelled as being 6 centimetres long and another as 8 centimetres long. We can use Pythagoras' theorem to find the value of x, the length of the third side. Well, the theorem states that h squared is equal to a squared plus b squared. The first step is to identify the values of h, a and b. H refers to the hypotenuse, which is the side across from the right angle. In our triangle, this corresponds to x. A and b refer to the other two sides, and these can be assigned in either order. In our triangle, we can let a be 8 and b be 6. Putting these values into our formula tells us that x squared is equal to 8 squared plus 6 squared. 8 squared is equal to 64 and 6 squared is equal to 36. 64 plus 36 gives us 100, which tells us that x squared is equal to 100. To find the value of x, we must remove the squared operation. We do this by taking the square root of both sides of the equation. The square root of x squared is just x, and the square root of 100 is 10. So our final answer is that x equals 10 centimeters. Let's take a look at another example. This time the sides are labelled as 16.4 centimeters, 14.9 centimeters, and x. The hypotenuse, h, is located across from the right angle. This corresponds to the x. The other two sides get labelled with a and b. Here we can set a equal to 16.4 and b equal to 14.9. Putting these values into the statement of the theorem tells us that x squared equals 16.4 squared plus 14.9 squared. Using our calculator to compute the right-hand side, we see that x squared equals 490.97. Like before, we can remove the squared operation by taking the square root of both sides. Using our calculator again to compute the square root on the right-hand side tells us that x is approximately equal to 22.2 centimeters. Let's have a go at one final example. In this triangle, the sides are labelled as 8.9 centimeters, 7.3 centimeters, and x. To identify the hypotenuse, h, we look across from the right angle. In this triangle, h is equal to 8.9. The other two sides should be labelled with a and b. Here we can set a equal to 7.3 and b equal to x. When we put these values into the statement of Pythagoras' theorem, we get 8.9 squared is equal to 7.3 squared plus x squared. This looks a bit different from the first two examples, and that's because the unknown side, x, does not correspond to the hypotenuse of the triangle. To solve this equation, we should start by simplifying things with our calculator. 8.9 squared equals 79.21, and 7.3 squared equals 53.29. In order to isolate our x term, there's two things we need to remove from the right-hand side. The plus 53.29 term and the squared operation. To remove the plus 53.29, we must subtract 53.29 from both sides. Calculating the left-hand side tells us that 25.92 equals x squared. Now, to remove the squared operation, we must square root both sides. Rounded to one decimal place, this brings us to a final answer of x equals 5.1. To summarise, there's two key skills required to apply Pythagoras' theorem. Skill 1 is to look at the triangle, correctly identify the values of h, a, and b, and then use these values to create a mathematical equation. Skill 2 is to use your knowledge of algebra to solve the resulting equation. To finish this video, we'll use some quick-fire multiple-choice questions to help you practice skill 1. Then, I'll present 2 longer exercises which you can use to practice both of our skills together. As promised, here's 2 exercises for you to try. Get out some pen and paper and give them a go. The answers are included in the video description, so feel free to have a peek at these whenever you're done working. Hello and welcome. In this episode, we're covering the SOHCAHTOA method for right-angled triangles. To begin, let's familiarise ourselves with some key terminology. The Greek letter theta is often used to represent an unknown angle in a triangle. Given an angle theta in a right-angled triangle, it is possible to label the 3 sides of the triangle with the following terms: hypotenuse, opposite, and adjacent. The hypotenuse is the side across from the right angle. The opposite is the side across from our angle theta. The adjacent is the side which touches theta and isn't the hypotenuse. Let's get some practice applying these definitions. We've got some practice identifying the hypotenuse, opposite, and adjacent. This is a crucial building block when it comes to the trigonometric functions sine, cos, and tan, since each of these is defined as a ratio of these quantities. The sine of theta is defined to be the opposite over the hypotenuse. The cos of theta is the adjacent over the hypotenuse, and the tan of theta is the opposite over the adjacent. A nice way to remember these results is to focus on the first letter of each word. S for sine, O for opposite, and H for hypotenuse gives us SOH. C for cos, A for adjacent, and H for hypotenuse gives us CAH. T for tan, O for opposite, and A for adjacent gives us TOA. Putting these all together gives us the word SOHCAHTOA. If you can remember this word, it will help you recall the definitions for sine, cos, and tan. Some people like to turn the word into a sentence, and there's many ways to do this. My personal favourite is, silly old Harry chased a horse through our attic. Now, let's see some examples of SOHCAHTOA in action. In this triangle, one angle is labelled as a right angle and another angle is labelled as theta. The three sides are labelled 3, 4 and 5. To find the sine, cos and tan of theta, the first step is to label each of our three sides. The hypotenuse is the side across from the right angle. Here, that's 5. The opposite is the side across from the angle theta. Here, that's 4. The adjacent will just be whichever side is left over. Here, that's 3. Well, by definition, sine of theta is equal to the opposite over the hypotenuse. Since the opposite is 4 and the hypotenuse is 5, the sine of theta will be equal to 4 over 5. Cos of theta is the adjacent over the hypotenuse. In our triangle, the adjacent is 3 and the hypotenuse is 5, so cosine of theta will be equal to 3 over 5. Tan of theta will be equal to the opposite, 4, over the adjacent, 3. Here's another example. In this triangle, the hypotenuse is equal to 10.1. The opposite is 5.8. And the adjacent is 8.3. Sine of theta is equal to the opposite, 5.8, over the hypotenuse, 10.1. Cos of theta will be the adjacent, 8.3, over the hypotenuse, 10.1. Tan of theta will be the opposite, 5.8, over the adjacent, 8.3. Now that we have a good grasp of our three trigonometric ratios, let's see how they can be used to solve for an unknown value in a right angle triangle. In our first example, we are given an angle of 38 degrees, a right angle, and a side length of 12.3. We must find the value of x rounded to 1 decimal place. In the SOHCAHTOA method, there are 3 options available to us: sine, cos and tan. To figure out which one to use, we should begin by labelling the three sides of the triangle. The hypotenuse is the side across from the right angle. The opposite is the side across from the 38-degree angle. And the adjacent is the third side that remains. In our triangle, the opposite corresponds to x, and the adjacent corresponds to 12.3. However, the hypotenuse doesn't correspond to anything. Since we have information on the opposite and adjacent, we should use the ratio which involves these two quantities, and that's tan. Another way to think of this is that we have no information or interest in the hypotenuse, so we should make sure that this isn't involved in our ratio. Since sine and cos both involve the hypotenuse, these two options are ruled out. So, we've decided that we'll use the statement tan of theta equals the opposite over the adjacent. In our triangle, the angle theta is equal to 38 degrees. The opposite is x, and the adjacent is 12.3. To solve for x in this equation, we need to remove the division of 12.3 from the right-hand side. We can do this by multiplying both sides by 12.3. Performing the calculator work on the left-hand side and rounding to one decimal place gives us the answer that x is equal to 9.6. In our second example, we have a right-angle triangle which contains an angle of 26 degrees. The hypotenuse is labelled x, the opposite is not labelled at all, and the adjacent is labelled as 9.1. Since we have labels for the hypotenuse and adjacent, we should use the ratio that involves these two quantities, cos. Plugging in the values for our triangle tells us that cos of 26 is equal to 9.1 over x. Solving for x is a bit trickier here, and that's because the x appears beneath the line in a fraction. As the first step, we can multiply both sides by x to get rid of this division. From here, all we need to do is remove the multiplication by cos of 26. We do this by dividing both sides by cos of 26. Performing the calculation on the right-hand side and rounding to one decimal place gives us the answer that x equals 10.1. In our final example, we have a right-angle triangle and one of the other angles is labelled as x. The hypotenuse is labelled as 5 and the side opposite x is labelled as 4. The adjacent does not have a label. Since we have labels for the opposite and hypotenuse, we should use the statement which involves these two quantities. Sine of theta equals the opposite over the hypotenuse. In our triangle, theta corresponds to x, the opposite is 4, and the hypotenuse is 5. So the statement becomes sine of x is equal to 4 over 5. To solve for x, we need to remove the sine function in front of the x. We do this by taking sine inverse of both sides of the equation. On the left, the sine inverse cancels with the sine, and we're just left with x. Now we can use our calculator to compute the right-hand side. Rounded to one decimal place, we find that x equals 53.1 degrees. Now that we've seen some examples, it's time to get some practice yourself. To conclude this episode, here are 2 exercises that you can attempt using pen and paper. The answers to these exercises can be found in the video description. Hello and welcome. In this episode, we're exploring the Sine Rule, a useful method which can be applied to any sort of triangle, not just right-angled ones. The key to unlocking this powerful method is grasping the concept of side-angle pairs. Let's begin by explaining this idea. Every triangle has 3 angles and 3 sides. For example, this triangle has angles of 47, 68 and 65 degrees. It has side lengths of 9.6, 8 and 10. Each of the angles can be paired off with the side across from it. If we look across from the 47 degree angle, we hit the side of length 8. So the first side angle pair is 847. Looking across from the 65 degree angle, we reach the side of length 9.6. So the second side angle pair is 9.6, 65. Finally, going across from the 68 degree angle hits the side length of 10. So the third side angle pair is 10, 68. Along with an understanding of side angle pairs, it's also crucial to get comfortable with the following naming convention. Angles are labelled with capital letters and the opposing sides are labelled with the lowercase versions of the same letter. Let's illustrate this. Angles should be labelled with capital letters. So in this first triangle, I'll label the angles with capital A, capital B, and capital C. The side across from capital A should be labelled with lowercase a. The side across from capital B should be labelled lowercase b, and the side across from capital C should be labelled lowercase c. In the second triangle, I'll label the angles with the capital letters P, Q and T. The sides across from these angles should be labelled with lowercase p, q and t. Before we introduce the statement of the sine rule, let's take some time to test your knowledge of side angle pairs. The sine rule states that, given two side angle pairs, A capital A and B capital B, we have the following. A over sine of capital A equals B over sine of capital B. The sine rule involves four quantities, two sides and two angles. If we know 3 out of the 4 quantities, then the sine rule will give us an equation which can be used to solve for the last quantity. Let's get some practice. In this triangle, we have one complete side angle pair, the 74-degree angle and the side of length 24. Let's label these with capital A and lowercase a. There's also another side angle pair labelled, the angle of 30 degrees and the side of x. Remember, the angles should always be labelled with capital letters and the sides with lowercase letters, so here let's label the angle with capital B and the side with lowercase b. The sine rule says that A over sine of capital A equals B over sine of capital B, so putting our values into the statement tells us that 24 over sine of 74 equals x over sine of 30. From here, algebra could be used to solve the equation and find the value of x. However, before we turn our attention to the algebra, let's get some more practice using the sine rule on some other triangles. In this triangle, the 28-degree angle and the side of 31 form a side angle pair. Let's label these capital A and A. The 125-degree angle and x also form a side angle pair. Let's label these capital B and B. Putting these values into the statement of the sine rule tells us that 31 over sine of 28 equals x over sine of 125. In our final example, the 36-degree angle and the side of 5.4 form a side angle pair. The angle of x and side of 9.2 also form a side angle pair. These can be labelled with capital A, A, and capital B, B. If we plug these values into the sine rule, we get the equation 5.4 over sine of 36 equals 9.2 over sine of x. We are now ready to see the sine rule in action from start to finish. The first step, which we've already practiced, is to correctly label the diagram and create an equation. The second step will be to use algebra to solve the resulting equation. In our first example, we have a triangle which contains angles of 42 degrees and 71 degrees. One side is labelled 14.7 and another side is labelled x. These four values form two side angle pairs. The 71 degrees pairs with the 14.7 and the 42 degrees pairs with the x. We should label these pairs capital A, capital B, B. The sine rule states that A over sine of capital A equals B over sine of capital B. Writing in our values tells us that 14.7 over sine of 71 equals x over sine of 42. To isolate the x, we'll need to get rid of the division of sine 42 on the right-hand side. We can do this by multiplying both sides by sine of 42. Typing the entirety of the left-hand side into our calculator and rounding to one decimal place, we get an answer that x equals 10.4. In our second example, we have a triangle with side lengths of 7.3 and 12.1. One of the angles is 82 degrees and another of the angles is labelled x. Again, these four quantities form two side angle pairs. This is precisely the scenario where the sine rule can be applied. The first pair is an angle of 82 degrees and a side of length 12.1. We label these capital A and A. The second pair is an angle of x and a side of 7.3. We label these with capital B and B. Putting these values into the statement of the sine rule tells us that 12.1 over sine of 82 equals 7.3 over sine of x. This equation is a bit more difficult to solve. The first issue is that the x appears beneath the line in a fraction. A nice trick to get it out of here is to flip both sides of the equation. From here, there's two things we need to remove in order to isolate the x. The sine function in front of the x and the division by 7.3. We'll begin by getting rid of the division, and we can do this by multiplying both sides by 7.3. As the next step, we can simplify the left-hand side using our calculator. Now, to get rid of the sine function, we should take sine inverse of both sides. Turning to our calculator again, we can compute the left-hand side to see that x equals 36.7 degrees. To finish off this episode, get out some pen and paper and have a go at these two exercises. The answers can be found in the video description. Hello and welcome to episode 4 of our Trigonometry Made Easy series. Today, we're diving into the cosine rule, a technique that relates the three side lengths of a triangle to the cosine of one of its angles. This versatile method applies to all triangles, not just right-angled ones. Let's jump straight into the statement of the theorem. Given the three sides A, B, C, and the angle capital A, we have A squared equals B squared plus C squared minus 2BC times the cosine of capital A. An important thing to be aware of here is the naming convention. Angles in a triangle are labelled with capital letters, and the side opposite each angle is labelled with the corresponding lowercase letter. When applying this result, it's crucial that the side labelled with lowercase a is opposite the angle labelled capital A. The letters B and C play symmetric roles, and they can be assigned to the other two sides in either order. Let's take a look at some examples. In this triangle, the three sides are labelled as 18, 16, and x. We have an angle labelled as 30 degrees. The cosine rule only involves one angle, capital A. In our diagram, we only have one angle labelled, the 30 degrees, so this will correspond to capital A. The side opposite this angle should be labelled with lowercase a, and in our triangle, that's going to be the x. B and C can be assigned to the other two sides in either order. Here, I'll let B equal 18 and C equal 16. The cosine rule states that a squared equals b squared plus c squared minus 2 times b times c times the cosine of capital A. Since a equals x, b equals 18, c equals 16, and capital A equals 30, this becomes x squared equals 18 squared plus 16 squared minus 2 times 18 times 16 times the cosine of 30. From here, we could use some algebra to find the value of x. However, before we turn our attention to the algebra, let's see a couple more examples of forming equations with the cosine rule. In this triangle, the sides are labelled 9.3, 7.2, and x. One of the angles is labelled as 41 degrees. We should label the angle with capital A and the side opposite as lowercase a. The other two sides should be labelled B and C. Here, I'll let B equal 9.3 and C equal x. When we put these values into the statement of the cosine rule, the a squared becomes 7.2 squared, b squared becomes 9.3 squared, c squared becomes x squared, and the 2bc cosine of a becomes 2 times 9.3 times x times cosine of 41. In our final example, the three sides are labelled as 4.8, 10.9 and 8.5. One of the angles has been labelled as x. We should label the angle x with capital A. The side opposite, 8.5, gets labelled with lowercase a. The other two sides, 4.8 and 10.9, get labelled with B and C. When we write these values into the cosine rule, we get the following. 8.5 squared equals 4.8 squared plus 10.9 squared minus 2 times 4.8 times 10.9 times the cosine of x. Now that we've seen some examples, it's time to test your knowledge on what we've learned. Successfully applying the cosine rule involves two steps. First, we must correctly label the diagram and extract an equation. Second, we should use algebra to solve this equation. Let's see these two steps in action together. In our first example, we have three sides labelled: 9.6, 7.1, and x. We also have an angle of 67 degrees. Well, the cosine rule involves three sides and one angle, and that's precisely the setup we have here. We label the angle as capital A and the side across it as lowercase a. The other two sides get labelled with B and C. Here we have A equal to x, B equal to 7.1, C equal to 9.6, and capital A equal to 67. Subbing these values into the cosine rule gives us the equation x squared equals 7.1 squared plus 9.6 squared minus 2 times 7.1 times 9.6 times the cosine of 67. Even though the right-hand side looks a bit messy, it doesn't involve any unknowns, so we can type the whole thing directly into our calculator. This tells us that x squared equals 89.3055. To isolate the x term, all we have to do is remove the square operator. We do this by taking the square root of both sides. When we perform the calculation on the right-hand side, we find that x equals 9.5. In our second example, the three sides are 5, 6, and 8. One of the angles is marked as x. To begin, we need to label our diagram appropriately. The angle should be labelled with capital A, and the side opposite this angle as lowercase a. The other two sides are labelled with B and C. This can be done in either order. Here we have capital A equal to x, A equal to 6, B equal to 5, and C equal to 8. Putting these values into the statement of the cosine rule tells us that 6 squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times the cosine of x. Solving this equation will require several steps. To begin, we can simplify things by performing some computations. 6 squared equals 36. 5 squared plus 8 squared comes out to 89. And 2 times 5 times 8 equals 80. Now, to isolate the x, there's 3 layers we need to strip away. The cosine function, the multiplication of minus 80, and the addition of 89. To remove the addition of 89, we should subtract 89 from both sides. On the left, 36 minus 89 simplifies to minus 53. To remove the multiplication of minus 80, we should divide both sides by minus 80. To get rid of the cosine function, we should take cosine inverse of both sides. Typing the left-hand side into our calculator brings us to our final answer. X equals 48.5 degrees. To conclude this video, it's time for you to get some of that all-important practice. Try these 2 exercises using pen and paper. The answers can be found in the video description. Hello and welcome to episode 5 of our Trigonometry Made Easy series. Over the course of the previous episodes, we've covered the 4 main trigonometry methods: Pythagoras Theorem, SOHCAHTOA, the Sine Rule, and the Cosine Rule. With so many options available, a natural question arises. How do we know which method we should use? This is a task that many students struggle with, and in this video, we'll take a deep dive into exactly how we can overcome this challenge. In our analysis, we'll focus on 2 crucial questions. First, does the method require a right-angled triangle? And second, how many sides and angles are involved? As we'll see later, being able to answer these questions is the key to correctly choosing the appropriate strategy. Let's begin by overviewing and analysing each of our 4 methods. Pythagoras' theorem states that in a right-angled triangle with a hypotenuse of length h and lengths of a and b for the other 2 sides, we will have h squared equal to a squared plus b squared. This method can only be applied to right-angled triangles. Our diagram involves 1, 2, 3 sides and 1 angle, namely the 90-degree angle. To apply the SOHCAHTOA method, we must have a right-angled triangle which has another angle, theta, marked in. The side across from the right angle gets labelled h for hypotenuse. The side across from theta is labelled O for opposite. And the third side is labelled A for adjacent. There's 3 ratios to choose from in this method. Sine of theta equals the opposite over the hypotenuse. Cos of theta equals the adjacent over the hypotenuse. And tan of theta equals the opposite over the adjacent. Each of these statements involves one angle, theta, and two of the three sides. If you also include the right angle, in total we have two sides and two angles involved. The sine rule is a versatile method which does not require the triangle to contain a right angle. Given two side angle pairs, capital A, A, and capital B, B, we have the following. A over sine of capital A equals B over sine of capital B. In total, this involves 1, 2 sides and 1, 2 angles. The cosine rule is also a general method which does not require a right angle. Given an angle, capital A, and the three sides, A, B, C, we have A squared equal to B squared plus C squared minus 2BC times the cosine of A. Counting the sides and angles, we have 1, 2, 3 sides and 1 angle. When presented with a triangle, the first question to ask is whether or not it contains a right angle. The second thing to investigate is how many sides and angles are involved. Considering the case of a right angle triangle, if 3 sides and 1 angle are involved, then we should use Pythagoras' theorem. On the other hand, if 2 sides and 2 angles are involved, then we should use the SOHCAHTOA method. In the case of a non-right angle triangle, 2 sides and 2 angles indicates that the sine rule should be used. 3 sides and 1 angle suggests that the cosine rule should be applied. One thing to keep in mind here is that when we are counting the number of sides and angles, we should include the unknown value and the right angle, if there's one present. Now that we've nicely laid out our decision tree, let's see some examples of this process in action. In this triangle, we have the 3 sides labelled as 7.7, 6.9 and 8.6. One of the angles is marked as X. So, which of our 4 strategies is suitable here? Well, first we should check for the presence of a right angle, and this triangle doesn't have one. Immediately, this restricts our possibilities to either the sine rule or cosine rule. Next, we should count the number of sides and angles labelled, including the unknown X. We have 1, 2, 3 sides and 1 angle. The sine rule requires 2 sides and 2 angles, whereas the cosine rule requires 3 sides and 1 angle. Since we have 3 sides and 1 angle, we'll want to opt for the cosine rule. In our second example, we have a triangle with sides of 7, 8 and X. one of the angles is marked as being 90 degrees. First, we should check if we have a right angle. In this triangle, we do, since by definition, a right angle is one which measures 90 degrees. This immediately reduces the possibilities down to either Pythagoras' theorem or the SOHCAHTOA method. Now, we should count how many sides and angles are involved, ensuring that we include both the unknown x and the right angle. We have 1, 2, 3 sides and 1 angle. SOHCAHTOA requires 2 sides and 2 angles, which we don't have. Pythagoras requires 3 sides and 1 angle, which is precisely what we have. So the winner here is Pythagoras' theorem. In our third example, we have sides of 18 and 30. We also have angles of 110 degrees and x degrees. The triangle does not contain a right angle. This means we'll want either the sine rule or cosine rule. Counting our sides and angles, we have 1, 2 sides and 1, 2 angles. The sine rule involves 2 sides and 2 angles, so this is the correct choice. In this triangle, we have an 87-degree angle and sides of 8.2, 11.8 and x. The triangle does not contain a right angle. The diagram involves 3 sides and 1 angle. This is the setup for the cosine rule. This triangle has sides of x and 12. It has angles of 90 degrees and 50 degrees. We do have a right angle present, and all in all, we have 2 sides and 2 angles. This means we should use the SOHCAHTOA method. In our final example, we have sides of 14, 18 and x. We have angles of 90 degrees and 40 degrees. Our triangle does contain a right angle, and this restricts us to either Pythagoras' theorem or the SOHCAHTOA method. The labels involve 1, 2, 3 sides and 1, 2 angles. Pythagoras requires 3 sides and 1 angle, whereas SOHCAHTOA requires 2 sides and 2 angles. As it turns out, our triangle fits both of these requirements. One option would be to ignore the 40-degree angle and then apply Pythagoras. Another option would be to ignore one of the sides, say the 14, and then apply SOHCAHTOA. Hopefully these examples have helped you get a grasp on the procedure for correctly choosing what method to apply. To finish off this video, I'll present several short exercises to give you an opportunity to get some of that all-important practice. Hello and welcome to the 6th episode of our Trigonometry Made Easy series. In the previous episodes, we've covered a variety of trigonometric methods and techniques. In this episode, we will complete the puzzle by putting everything together, demonstrating how to overcome trigonometry problems with confidence and ease. In the problems that follow, we can break up our solution into 3 distinct steps. The first step is to identify your strategy. There's 4 main methods to choose from here: Pythagoras Theorem, the SOHCAHTOA method, the Sine Rule, and the Cosine Rule. Once we've chosen our method, step 2 is to label the diagram appropriately and apply the chosen result to form an equation. Step 3 is to use algebra to solve the resulting equation. By focusing on these steps one at a time, even the most complex problems will be broken into much more manageable chunks. Without further ado, let's jump into some examples to see this process in action. In our first example, we have a triangle with sides of 16.5, 18.1 and x. We also have a 69-degree angle. To solve for x, the first step is to identify which method to use. A very useful question to ask here is the following: does the triangle contain a right angle? Pythagoras and SOHCAHTOA require a right angle, whereas the sine rule and cosine rule do not. Since our triangle does not have a right angle, we'll want to use either the sine rule or cosine rule. Now, we should look at how many sides and angles are labelled in the diagram, including the unknown x. The sine rule requires 2 sides and 2 angles, whereas the cosine rule needs 3 sides and 1 angle. In our diagram, we have 3 sides and 1 angle. So here we'll need to opt for the cosine rule. This states that a squared equals b squared plus c squared minus 2bc times the cosine of a. Now that we've identified our method, step 2 is to label our diagram and form an equation. The capital A in our statement refers to the angle. Here, that's 69. Lowercase a corresponds to the side across from this angle, which is x. B and C refer to the other 2 sides, and these can be assigned in either order. Let's let B equal 16.5 and C equal 18.1. When we put in these values, the a squared becomes x squared, the b squared becomes 16.5 squared, and the c squared becomes 18.1 squared. The 2bc cosine of a becomes 2 times 16.5 times 18.1 times the cosine of 69. Now that we formed our equation, our third and final step is to use some algebra to solve for x. While looking a bit complicated, the right-hand side of our equation does not contain any unknowns, so we can simplify by typing the whole thing into our calculator. This tells us that x squared equals 385.8068. To isolate the x, all we need to do is remove the squared operator. We do this by doing the inverse operation, which is square rooting. Typing the right-hand side into our calculator tells us that x equals 19.6. In our second example, we have side lengths of 3.7 and x. One of the angles is marked as a 90-degree right angle, and another is marked as being 46 degrees. The presence of a right angle means that we'll want to use either Pythagoras or SOHCAHTOA. Pythagoras' theorem involves all three sides of the triangle, but we only have two of the three sides labelled, so this won't be an option. By process of elimination, we'll want to use SOHCAHTOA. There's three ratios to choose from in this method: sine, cos and tan. To figure out which one to use, we should label the sides of our diagram. The hypotenuse is the side across from the right angle. The 46-degree angle should be labelled theta, and the side across from this is labelled as the opposite. The third side is labelled as the adjacent. In our diagram, the opposite corresponds to x, the hypotenuse corresponds to 3.7, and the adjacent does not correspond to anything. Hence, we'll want to choose the ratio which involves the opposite and the hypotenuse. In other words, we should use the statement that sine of theta equals the opposite over the hypotenuse. Putting in the values for our triangle tells us that sine of 46 equals x over 3.7. To solve for x, all we need to do is remove the division of 3.7 from the right-hand side. We do this by multiplying both sides by 3.7. We can type the left-hand side into our calculator to get our final answer. X equals 2.7. In our final example, we are presented with a quadrilateral and asked to find the values of two unknowns, x and y. We have sides labelled with 12, 5 and 9.2. We also have a 90-degree right angle and a 97-degree angle. Let's start by finding the value of x. A key observation here is that our shape can be split into two different triangles, which I've coloured in blue and red. The side labelled x appears in both of these triangles, so we'll need to think about which one of these to focus on. Well, in general, the more things you know, the easier it is to figure out the things you don't know. In the blue triangle, we know two sides, the 12 and the 5. We also know one angle, the 90-degree right angle. So in total, we have 3 known values. In the red triangle, we only know 2 quantities, the side length of 9.2 and the angle of 97. We do have another angle labelled as y, but since we don't know the value of y, it's not much good to us. Since we know more information in the blue triangle, it'll be wise to focus here. Since our triangle contains a right angle, we'll want to use Pythagoras or SOHCAHTOA. Focusing on the sides, we'll notice that all three sides are involved. This is the perfect setup to apply Pythagoras. This states that h squared equals a squared plus b squared. H refers to the hypotenuse, which is the side across from the right angle. A and b refer to the other two sides. Here, we can let h equal to x, a equal to 12, and b equal to 5. Putting these values into our statement tells us that x squared equals 12 squared plus 5 squared. This equation can be solved to find the value of x. Let's begin with some calculations. 12 squared equals 144, and 5 squared equals 25. When we add these two values, we see that x squared equals 169. Now, to isolate the x, we need to remove the square operator. We do this by taking the square root of both sides. The square root of x squared simply comes out as x, and the square root of 169 is equal to 13. So our final answer is that x equals 13. Now that we've found x, we can turn our attention to y. Again, we'll need to pick which of the two triangles to focus on. However, the decision is easy here. We'll want to pick the upper triangle since this is the only one which contains the angle y. This triangle does not contain a right angle. This limits us to either the sine rule or the cosine rule. To distinguish between them, we should count up how many sides and angles are involved. In our triangle, we have 2 sides and 2 angles. This is the setup for the sine rule. A over sine of capital A equals B over sine of capital B. To apply this statement, we should first label our diagram. We label our first side angle pair as capital A, little a. We label our second side angle pair as capital B, little b. Here, capital A equals 97, little a equals 13, capital B equals y, and little b equals 9.2. When we input these values into the sine rule, we get 13 over sine of 97 equals 9.2 over sine of y. From here, we can use some algebra to find the value of y. It's a little bit awkward having the y underneath the line in a fraction, so let's begin by flipping both sides of the equation. Next, we can remove the division of 9.2 by multiplying both sides by 9.2. Typing the left-hand side into our calculator, we see that 0.7024 equals the sine of y. Now, to remove the sine function from the right-hand side, we should take the inverse sine of both sides. Typing the left-hand side into our calculator brings us to our final answer. Y equals 44.6 degrees. To finish off this video, it's time for you to try some exercises using pen and paper. The answers can be found in the video description.